All right, everybody hear me okay?
Yep.
All right, everybody see my screen?
Yep.
All right, because sometimes I forget to record and sometimes I forget to share. So I'm trying to be a nice person and share. So there you go. All right, we'll get started in half a minute here. As soon as I see 3:30 on the clock. Okay, I got 3:30, guys. So let's go ahead and get started. So just a couple reminders moving forward, looking forward. Everybody see the homework that's posted. Hopefully you did. That's over at D2L. And it's a buffer assignment. So that's your buffer homework. It's due next Tuesday. So be aware of that. Also, of course, the kombucha lab is due next Tuesday, which you guys did last night. So keep in mind with that buffer assignment, when you go look at it, I'm sure some of you guys probably already have, each individual person has a different pH buffer to make. Okay, so it's not just one problem, everybody's working the same problem. Well, essentially you are, but everybody has a different pH and a different change in pH to do. This is actually usually a lab we do where we actually have you do those calculations in advance. And then we go in the lab and actually make the buffer. But I replaced that lab with the kombucha alcohol lab. And I now dry lab the buffer one. So that's why we do it for homework. So that'll be your last buffer assignment to do.
So quick question.
Yeah, go ahead.
For the syllabus, should we then read 9.1 through 9.6 and then read chapter 13 for next week? Because I assume we're keeping on with the syllabus then, and we're going to do the hard water analysis.
You got it.
Okay.
Yep, you got it. So that's the next thing. That's what we'll actually start into today is discussion of the hard water analysis. So yep, that's the next one. So probably by tomorrow, I'll have that new lab posted for you. So yes, the next lab is the complex symmetric EDTA hard water titration lab. It's a very simple 1 week lab. So we're actually doing a series of 1 week labs now for a while. And then we'll finish out the semester with a big long 3 week lab. So we're into 1 week labs now for a little bit. All right, good question. Says, yeah, I did change that up a little bit. So yeah, we introduced the new kombucha lab, which I wasn't sure whether I was going to do or not when I wrote up the syllabus. Well, apparently we did. By the way, I thought it went really well last night. And I think you guys actually enjoyed it. So, you know, didn't seem like it was terribly difficult for anybody. And it was just at least something a little bit different to do. Any thoughts on it, by the way? Just giving you guys are sort of the inaugural group to do it. Do you like it?
I thought it was good fun. Yeah, it was good fun.
Yeah, I thought so too. I enjoyed it. And it was quick too, so that's kind of nice. All right, so what I want to start in today is discussion of the next lab we're doing, which involves a complex symmetric titration. Now, in a complex symmetric titration, the name doesn't suggest that it's complex in the sense that it's hard to do, even though we will be analyzing hard water. It really has more to do with the fact that we're going to form a complex ion. Okay, so that's what the complex part means. Okay, so in this kind of titration, normally the analyte is going to be a metal ion. It could be almost any metal ion. In our case, we're going to be looking at calcium 2+. Okay. And the titrant is going to be a ligand. And the specific ligand that we are going to use is EDTA 4-. Okay, so EDTA stands for ethylene diamine tetraacetic acid or tetraacetate, depending upon whether it's in its protonated or deprotonated state. All right, so obviously when you have a metal ion and you got a ligand like EDTA, you're going to let those things combine with each other. You're going to make a complex or a complex ion. So it kind of harkens back to some of the very first stuff that you guys did in dynamics. So remember, quant is dynamics turned on its head, right? So now that we're getting later in quant, you're going to be reviewing stuff that you did earlier in dynamics. All right, so since we're just kind of coming off acid-base chemistry, I mentioned to you, I think, when we were doing the acid-base stuff, that we actually had 3 definitions of acid-base reactions, right? We had the Arrhenius definition, which is kind of the bonding level, high school level definition. And then we had the Arrhenius definition, or sorry, the Bronsted-Lowry definition. And that's the one that we used pretty much exclusively in this class. And you guys will use a lot in dynamics when you get to acid-base chemistry. And that's the one where we talked about, pitching and catching the proton, right? So the acid pitches the proton, the base catches the proton. So it's a simple proton transfer type of reaction where the acid gives up the proton, the base accepts the proton, right? And then I think I mentioned to you that there's one more type of acid-base reaction, and it's called the Lewis acid-base definition. And you'll remember when we talked about the other definitions, we said that with each new definition we brought on, we're talking about a more general definition of acid-base chemistry, right? We said that in a sense, the Arrhenius definition was the most restrictive, and then we could eliminate a lot of those restrictions by going to the Bronsted-Lowry definition. Okay, but now the Lewis acid-base definition is the one that's most general. So what this does is it opens up a whole new class of acid-base reactions that we never even knew were acid-base reactions before. So here are the definitions. All right, a Lewis acid is going to be an electron pair acceptor. And a Lewis base is going to be an electron pair donor. So this sounds a lot like it has to do with making and breaking bonds, doesn't it? Okay. So let's take a look at an example of this. So let's look at something that we normally think of as like a Bronsted-Lowry acid-base reaction. So here's one that you guys have seen before. Okay, I could have something like ammonia, which is NH3. We'll put it in an aqueous solution. And I know that ammonia can accept a proton, and I'll just keep things simplified here by just letting the proton be a proton, as opposed to attaching it to water to make hydronium. And you guys know what's going to happen here. This is going to be the base. The proton is going to be the acid, obviously. Okay, remember that if you go back to the Lewis structure of NH3, you got an electron pair on that nitrogen. Okay, and that's one reason we said that these amine or nitrogen-based bases are good bases, because they have those electron pairs there that can accept a proton, right, from the acid. So the proton is electron deficient, so it needs an electron pair to form a bond into something. Okay, and notice the nitrogen there actually has that electron pair that can be donated to form that bond. So you guys know what you're going to make. You're going to end up making ammonium ion. Okay, and what we've done there is we've utilized that electron pair on the nitrogen from the ammonia to form that new bond to the hydrogen. So if you went back to your Lewis structures for this, you would know that the ammonium ion has a structure that looks like this, right? And it satisfies the octet rule around the nitrogen. And of course, the whole thing carries a 1+ charge. So you can see how you formed a bond between the hydrogen and the nitrogen. All right, so in that sense, from the Lewis perspective, which is the acid and which is the base? Who accepted the electron pair? Was it the hydrogen ion or the ammonia?
To me, it looks like the hydrogen ion had to accept because I mean it didn't have any electrons before.
Exactly. So it's the electron pair acceptor. So the base has to be the electron pair donor. So in this case, we can definitely see that we could treat this reaction as either a Bronsted-Lowry acid-base reaction, or we could treat it as a Lewis acid-base reaction. Okay, so see how both definitions apply here. All right, what about this? Can we have an acid-base reaction that doesn't involve any transfer of protons? Well, it turns out we can, according to this definition. So let's take a look at another reaction you've seen before. So I could have an electron deficient iron ion in solution. I can let that react with 6 cyanides. Okay, and cyanide carries a 1- charge. And you guys will probably remember that I can make an octahedral complex ion. Okay, so it looks something like this: Fe CN taken 6. All right, and then of course it's going to carry some charge. So the iron carries 3 plus, and each cyanide's bringing in a 1 minus. So it looks like that's going to carry a total of 3 minus charge on the ion, right? And that's an aqueous solution. So what I've done here is I've formed a complex ion between a metal and a ligand. Okay, so now does this satisfy the Lewis acid base definition? So again, think about what you've done here. If I go back and I write a Lewis structure for this thing, you know it's going to carry an octahedral geometry, right? Which I can draw here. So I have a cyanide here, I've got a cyanide here, I've got a cyanide here, one down here, one here. And by the way, we bond through the carbon because that pair of electrons is more accessible than the pair on the nitrogen. And the whole thing carries a 3 minus charge. So what have I done? I've just formed 6 bonds here, right? And remember, the iron ion is electron deficient. It doesn't have electrons to donate out, but the cyanide, each cyanide has a pair of electrons to donate in. So as a result, what would the iron be? The Lewis acid or the Lewis base?
It'd be the acid.
Yeah, it's going to be the acid. And that means the cyanide, since it's donating the electron pairs, has to be the base. Okay, but can I apply a Bronsted-Lowry or an Arrhenius definition to this?
No.
No, I can't. Okay, so see how this is the most general definition for acid-base chemistry I can have, because I can have a classification of acid-base reactions that involve no protons. Okay, there's no proton transfer going on here. There's no hydrogen ion being donated into solution. Okay, so you get the right idea here. So this is really kind of what we're going to look at. So I just wanted to make sure you guys were aware of that last acid-base definition. Even though I normally am not going to talk about this as an acid-base reaction, I'm going to really talk about it as just the formation of a complex or a complex ion. Again, just like you learned earlier on in the semester. All right. So again, for quantitative analysis, I've already sort of defined what the titrant is and what the analyte is. So again, to just re-recognize that, the analyte is going to be a metal ion of choice. In our case, it's going to be calcium ion because that's indicative of hard water. Okay. And the titrant or the ligand is going to be EDTA4 minus. By the way, do you guys remember what kind of a ligand EDTA is? We're going to talk about it in just a minute. Was it a monodentate, bidentate, polydentate? Do you guys remember?
Polydentate, right? Or no, it's
Yeah,
bidentate. Poly, it's 3, right?
Well, that would be tridentate. Poly
Okay.
can be multidentate, so it could be any number of coordination sites taken up. And we're going to see that in just a minute, how this is actually going to look. So we want to look more closely at EDTA. All right. As I mentioned, it's a polydentate ligand normally. All right, so I'm going to sort of borrow a figure out of the book. I'm going to just reproduce it here because, you know, it just kind of works out that way to do it. But here's what EDTA looks like. It's a nitrogen bonded to a CH2, bonded to a CH2, bonded out to another nitrogen. Okay, and then up and down from there, I'm going to have essentially a CH2, and then a carboxylic acid group. So that's going to be a C if I wanted to write it out, C double bond O to an O. And then I could have a hydrogen on here. So I'm going to go ahead and put this in the fully protonated form. So I'm going to do the same thing down here. All right, I'm kind of leaving the electron pairs out if that's okay by you guys. And then we have one up here. All right, now notice that I've got a proton here, 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 and there's 2 more places I could put protons. Because remember, each one of these nitrogens has an electron pair on it, right? They look like the same kinds of nitrogens that we would see, for example, in ammonia. So as a result, I can make another bond with a hydrogen here, and I can make a bond with a hydrogen here. Okay, so if I get this thing in the fully protonated form, I've got basically 6 places where I can put a proton, right? So if you can imagine a situation like this, where you think about this thing as like being a weak acid, how many protons could it give up if I start in the fully protonated state? Right, because we think about things like carbonic acid, which can give up 2 protons, right, sequentially, or phosphoric acid, which could give up 3. How many could this guy give up?
6.
6, yeah. So this thing has the potential to give up 6 protons. Now, when we talk about polyprotic acids like that, do they give up all the protons at once?
No.
No, it's a stepwise sequence, right? Because essentially each one of these has a Ka associated, right, with it, right? So we could say, you know, that first one, and we can be a little bit random about this, but we could say that first one might correspond to a Ka1. Here's a Ka2. There would be a Ka3. This guy would correspond to a Ka4. And then finally you go over to the amine ones, and that would be like a Ka5. Those are the ones that are hardest to get rid of, and Ka6. Okay. So essentially each one of those protons has a Ka associated with it. All right. So what that basically means is that each one of these has a pKa. Okay. And I'm just pulling from the book here. I could have pKa1, and that turns out to be at a value of 0.0. And I could have pKa2. That turns out to be a value of 1.5. And we could have pKa, and you could back calculate what these Kas actually are if you wanted to, because remember, a pKa is just a negative log of a Ka. That could be at 2.0, pKa4, and again, this is all in your book, is equal to 2.69, pKa5 is equal to 6.13, and pKa6 is going to equal to 10.37. So notice what happens. If we were to take EDTA and we were to put it into a successively more basic solution, right? Think about the pH and the pKa relating to each other, right? So I can think about this almost like a buffer, couldn't I? So if I had a pH of around 0 or lower than that, that tells me that this thing is going to be in the fully protonated state. But if I were to take EDTA and stick it into a pH of a solution around 11, really, really basic, it's going to be pretty much in the fully deprotonated state. Okay. And then if I have a pH around 7, okay, I'm probably going to be somewhere around pKa5. So that tells me I'm going to be mostly deprotonated. Okay, so everybody see what I mean by that? By essentially matching the pH and the pKa, I can pretty much predict what form this thing is going to be in. All right. Now the question then becomes, well, who cares and why does this all matter? Well, the reason why is because the degree of protonation or deprotonation is going to dictate how strong a complex we can form with a metal ion. Okay. So let me ask just a real theoretical question. Which do you think would bond more strongly with a metal ion like calcium? The fully protonated state or the fully deprotonated state of EDTA, and why?
Deprotonated because it has electron density to donate, whereas protonated already has paired electron.
Into a bond, right?
Yeah.
Yeah, that's exactly right. So in the form that I've showed you right here, fully protonated, all those electron pairs that we normally would use, okay, to donate into the ligand, or sorry, into the metal ion, are taken up with hydrogen ions, right? So I wouldn't be able to form a very stable complex or even a complex at all if I've done that, because I just don't have availability of electron pairs, polarizable electron pairs. They're all taken up. But if I were to run this thing up to a pH of like 10, 11, or 12, and I'm fully deprotonated, then all those hydrogen ions are gone, right? So then each one of those sites now has that electron pair available to donate in to the metal ion. So what that ultimately means is that I can make a much stronger complex at a greatly basic pH than I can at a neutral or acidic pH. Okay, does that make sense to everybody? And your explanation was perfectly correct there. Okay, so we'll just kind of put that down there. Okay, so we'll say to make a stronger complex, we need a more deprotonated form of EDTA. And we can achieve that by working at basic pHs. All right, in fact, when we actually do the experiment next week, one of the things we're going to add to the solution before we run the reaction is a buffer. And that buffer is going to be working up around 10.5 or 11, so at a very basic pH. And that's why we do it, because we want to form a very strong complex between the metal ion and the ligand. Okay, is that making sense to everybody? So this is interesting from the point of view that obviously we need to watch out for pH, because this ligand itself has acid-base properties. So even though we're not really thinking about this in terms of Bronsted-Lowry acid-base chemistry, we have to be aware of the form of the ligand that we've got before we ever introduce the metal ion. All right, any questions about that so far? Everybody good?
Yep.
Okay, so fully deprotonated, let's just take a look at what this would look like. So by the way, what would be the charge on this thing? So if I have an NH there, that's kind of like ammonium ion. So I'd carry a positive charge on that nitrogen. I'd carry a positive charge on that nitrogen. And then of course, with the protonated carboxylic acids, those are all neutral, right? So that's like acetic acid. Remember, it's in its protonated form, it's neutral. So that's kind of like what we're seeing there. So in the fully protonated form, the EDTA would actually be expressed as EDTA2 in the fully protonated form. Now, what if I were fully deprotonated? What charge would the EDTA ion have if I took all those protons away?
A 4-.
You got it, yeah. So fully deprotonated, which is where we normally use it, would be EDTA4-. Everybody see where that came from? All right, so that's the business form of EDTA is EDTA4-. And that's typically how we're going to show it when we actually talk about reactions happening. Okay, so here's the actual reaction. Let's just say we have this reaction. So let's say the metal ion we want to deal with is manganese 2+. Okay, so manganese 2+ can react at the proper pH with EDTA4-. Okay, and we have to think about this kind of as an equilibrium, don't we? Because that's just how we think about these things now. And we know what we're going to make. We're going to make the complex ion. All right, so what's the complex ion going to look like? Well, it's going to have a formula that looks like this. It's going to be Mn EDTA. Okay, what charge is the whole thing going to carry?
Two minus.
2-, okay, I agree with that. So that's the complex ion I make between manganese and EDTA. So notice, whenever we do this, it's one metal ion complexing with one EDTA ion, okay? And the reason for that is because this thing turns out to be hexadentate. So if you go back up to your EDTA up there and you fully deprotonate it, right? There's a site for protonation, or sorry, a site for complexation. There's a site for complexation. There's a site for complexation. There's a site for complexation. So all of those terminal oxygens on the carboxy groups. Oh, but remember, we also deprotonated those nitrogens. So there's a site for complexation, and there's a site for complexation. Count your check marks up. How many do you have?
6.
6. Okay. So basically what this means is that the geometry of this complex ion is what?
Oct.
Yeah, it's octahedral. I'm not going to try to draw it, but basically one EDTA is basically going to encircle the entire ion, manganese ion, and bind in through all 6 coordination sites to make an octahedral complex. Okay. So it's kind of interesting in that you've only got one metal and one ligand, but you're generating an octahedral complex. And that's because the EDTA in its fully deprotonated form has 6 coordination sites, right? So everybody make sure you can see that. And I think there's a picture in your book where you can actually go back and see how they kind of make a molecular model of this and show the EDTA basically wrapping itself around the ion. And you can sort of track that octahedral geometry that results from that. Okay. But as a result, this is going to be a very stable complex. Now, the other thing that we need to think about here is if we're dealing with equilibrium, this reaction is going to have an equilibrium constant or a big K value associated with it. So that K is called a K sub F. Okay, in the K sub F is called a coordination, is called a formation constant. So remember, we've experienced all kinds of Ks. We know about KSPs, those are solubility problems, and KBs if we're talking about weak acids and weak bases dissociating. So here's a new K, it's called a formation constant. And what it entails or describes is the formation of a complex or a complex ion between a metal ion and a ligand, okay? So you're going to run into that one in dynamics as well, but that comes later after you talk about all the other flavors of equilibrium constants. So you're going to do general equilibrium first. Maybe you guys have started it. And then you're going to talk about Kas and Kbs, and then you're going to go from there to KSPs, and then finally you're going to end up with formation constants. And that'll be toward the end of the semester. All right. Now, based on what I've already told you, would you expect a Kf to be a big value or a small value? In other words, should it be way greater than 1 or way less than 1 based on what I've already kind of told you about these complexes?
Would it be big?
Yeah, it's going to be really big. Okay, so KFs in general tend to be way, way, way larger than 1. So they tend to be very large. So it's not unusual for KFs to be on the order of 10 to the 5th, 10 to the 8th, 10 to the 20th, something like that. So remember how KSPs and Kas and Kbs tend to be small? Well, KFs tend to be really big, okay? Now, there's another variation of this that we can, and by the way, let's just go ahead and write the law of mass action out for this so we know what it looks like. So the Kf is going to equal to what? Products over reactants. So it's going to be the concentration of the manganese EDTA. I'm going to put the 2 minus inside, so I'm actually showing this as a concentration. So the brackets now represent molar concentrations, divided by the molar concentration of the manganese 2 plus times the molar concentration of the EDTA 4 minus, right? Products over reactants raised to their respective powers. And again, in this case, the products and reactants all have 1-to-1-to-1 stoichiometry. So that's what the KF would look like. And again, it's going to be a really big number. All right, I actually have it. I think I actually have the log of the KF here, which we could undo. Anybody actually got their calculator handy?
Yeah,
So
I
it turns
do.
out that the log, I'm just pulling this out of my notes. The log of the KF for the manganese one is 13.89. So take an anti-log of that and see what you get. What does the KF turn out to be for that? You just take the inverse log. It's going to be a really big ass number.
7.76 times 10 to the 13th. And I mean, 7 7.762 times 10 to the 13th, not negative.
Sorry, it
I
should be
got it
plus.
wrong. Yeah.
Yeah, it could be to the plus 13. Okay, so it's a really, really huge number. Okay, so that's not unusual for these things. As a result, I mean, I actually found this on the table that's in your textbook that has all these things in it. And they usually express them in terms of the positive log of the KF, again, to scale the number down a little bit so we don't have to put a bunch of really humongous numbers in here. So it's easier to write 13.89 down, and if you need to get a KF out of it, you just take the anti-log. Okay, just like we have done before in terms of relating like pKa's and Ka's, same idea. All right, so everybody good with this so far? Big numbers. So the equilibrium on these things lies way, way, way to the right because of the inherent stability of the complex or complex ion that we form relative to its ions. No other questions? Are everybody doing okay with this?
Yep.
All right, excellent. So let's just take a look real quickly at the one that we care about, right? So for us, here's the reaction. It's the calcium ion because now that's our analyte, because again, it's indicative of calcium carbonate, which is hard water. Plus EDTA, 4 minus. This is going to be, again, governed by a KF. And you know what we're going to make? We're going to make calcium EDTA. Oops, EDTA. What's the charge on the ion going to be?
-2.
2 minus. I'm just going to leave the brackets out because, again, when I want to make my law of mass action, I'll put it back in brackets to express molar concentrations. So that's calcium EDTA. 2 minus. And remember, all of these are equilibrium concentrations, right? So it's what we have at equilibrium. And again, I could look that up, and I found a log Ka and undid it. And this one, when I undo that, turns out to be a Ka value of 4.47 times 10 to the 10th power. Okay, so again, a really, really big equilibrium constant, which tells me about the inherent stability of the complex ion relative to its reactants. All right, so the nice thing about this, again, thinking about it from the perspective of a titration problem, right? Do I need to really worry about equilibrium in my titration?
No.
No, it's really just a limiting reactant problem because the K is so huge. It's kind of like those acid-base reactions that we talked about, where if you had a weak thing, you know, reacting with a strong thing, the assumption was the reaction goes 100% to the right. Okay, and if that happens, okay, well then you know that you don't have to worry about equilibrium. Okay, so the same thing is true here. We've got a really big K, so when we dump the EDTA into the solution containing the calcium, we know that reaction, for all intents and purposes, is going 100% to the right. And that's what we assume in a titration. Okay, that makes it quantitative for us. All right. Any other questions about that?
This is a little bit unrelated, but for EDTH, you know, ethylene diamine tetraacetate, we have all capital letters when we're writing it in our equation. Whereas like for ethanol, we had a capital E, a lowercase o, and then a TH. Is there any convention for that, or is it specific to each molecule?
It's specific to each molecule because again,
Okay.
this thing you're talking about ethyl alcohol being ETOH like that.
Yeah, I had it confused, but
Yeah,
like
that's
that.
really basically just an abbreviation for ethyl alcohol. So the E little t stands for ethyl. And then the OH part is the alcohol part. So that's where that name comes from. Okay.
Okay.
What does the ethyl mean? Well, it means an ethyl group, which is a CH3, CH2. That's the ethyl part. And then there's the OH, which is the alcohol part. So that's really more of an organic convention, right?
Okay, that makes sense. Thanks.
Yeah. So you guys haven't hit that yet, but whenever you see in organic chemistry a CH3, CH2 attached to something, oh yeah, you'll know that's an ethyl group. That's what you call that in organic nomenclature. Okay, so that's where that comes from. So it's a different kind of thing. The EDTA again is just again an abbreviation for ethylene diamine tetraacetate or acetic acid. So you're right, it's a convention that just kind of goes molecule by molecule, organic versus non-organic, even though EDTA is organic molecule when you get right down to it. All right, so here's another thing that we have to think about. And this kind of ties into the kombucha lab that we just finished, okay? And that has to do with selectivity. Now, where did selectivity come into play with the lab we just finished yesterday? If you think back to the lecture we had on Monday. What did selectivity mean there and why was it important and how did we achieve it? Does anybody remember?
Was it with the Teflon and it blocked out the water molecules?
Yeah, that's exactly right. So the problem is when we talk about a vapor pressure, we want our sensor to respond to only one specific molecule in the vapor, right? So if we assume in the case of our kombucha that we've just got a mixture of ethanol and water, okay, it would be nice if we could see the ethanol binding to the sensor, but not the water molecules. So our way of dealing with that was to put that Teflon tape over the sensor. So the Teflon tape, because of its non-polar behavior, blocked out the very polar water molecules, but allowed the ethanol molecules to pass through. Okay, so that's what I mean by selectivity. So if I've got a situation now where, let's say, I want to get the calcium ion, right? But let's say in like a real water sample, do you think calcium ion is going to be the only metal ion in there?
No.
No, probably not. I mean, actually, water is a tremendously complex matrix when you really get down to there. There's all kinds of stuff in water. So if you go get so-called spring water or well water or any of those kinds of things, you kind of just assume it's plain old H2O. Well, it's not. Okay, because think about it. That water could leach out minerals. That's what happens with hard water, right? Because it passes through something like limestone, which is calcium carbonate. And if the water is a little bit acidic, which happens because we have acid rain, right? It actually leaches away the calcium ion. So you have dissolved calcium ion and carbonate ion actually in the water. That's what constitutes hard water, okay? It can also be magnesium in there as well. That's another contributor to hard water. So calcium and magnesium are the two big contributors. But you could have those ions, you could have, depending upon what other minerals the water's been in contact with, as well as the pH of the water, you could have all kinds of other metal ions in there. You could have all kinds of anions in there. You can have organic matter in there, various organic acids, for example, from vegetation and decomposition of vegetation. Water is a very difficult matrix. There's a lot of stuff in there. So if you went and actually got a real water sample and you wanted to find, okay, what's the concentration of calcium in there? And you want to do it by way of a complex symmetric EDTA titration. How would you build selectivity into it, or could you build selectivity into it? What's our goal? Our goal in selectivity, if calcium is our analyte, our goal, obviously, is that the EDTA or minus react only with the calcium or react favorably with the calcium ion, which is our analyte. That's what we'd want, right? But remember, we also said that EDTA will bind a whole bunch of different metal ions, right? If you went back to your book in this chapter, you'd see a whole table full of metal ions that EDTA will bind to. Okay, I'm looking at it right here. I mean, it's like lithium, sodium, potassium, magnesium, strontium, scandium, yttrium, lanthanum, chromium. I mean, we're talking about main group metal ions. We're talking about transition metal ions. I mean, there's probably 50 or 60 different metal ions in here that EDTA will complex to. Okay. So if I have a collection of different metal ions in my solution, how can I set it up so that I can get the EDTA to bind preferentially with the calcium ion and not the other ones? See the problem I've got? I mean, it's a really big issue that we have to worry about. So that's what selectivity comes down to. And I like to talk about selectivity because it's a huge problem in general in analytical chemistry. We're not dealing with just a metal ion in water. We're dealing oftentimes with a whole bunch of different things in our matrix that could actually, in one way, shape, or form, affect the measurement that we want to make. Okay, so how do we make our measurement selective to the ion we want? All right, so, that's one thing we have to think about. So what's something right off the top of your head you might think about that we could just naturally use? Let's just say I had just a mixture of, say, calcium and maybe one other ion, just keep things really, really simple. I mean, what's one thing I could initially look at?
Solubility, and I don't know, maybe condense the solution to precipitate out anything else.
Yeah, that's actually a really good idea. I mean, if we could, for example, selectively precipitate out other species that are in solution by adding some sort of precipitating agent so that the KSP kind of rules out over the KF for those ions we don't want, that would be a really good idea because that would take them out of commission. It would put them in a solid down on the bottom of the beaker. And if they're down there, they can't react with the EDTA, right? That's a really good idea. But even if we backed up and did something even simpler than that, what we could do as a first sort of line of defense is we could compare KF values. Values, sorry. Can't spell today. All right, so let's say, for example, I want my calcium here. So I'm just going to remind myself of some values here. So log of KF, I'm just pulling directly out of this table for calcium. Let me look it up here. It's 10.65. All right, so let's say, for example, the other ion that we're worried about is potassium. Okay, well, I can look up a log KF for potassium. And it tells me here that the log KF for potassium is 0.8. Now, somebody take a calculator and turn those into KFs for me. And I don't care about sig figs. I just need some numbers here. What's calcium's KF?
4.47 times 10 to the 10th. And then we don't even really need to compare, I don't think, because just the order of magnitude is going to be so different.
Yeah, go ahead and give me a KF for the potassium ion nonetheless, just so I can see what it is. It's going to be pretty tiny.
Yeah, 6.3.
6.3. Okay, so look at this, guys. If I have only these two ions present and EDTA has a choice as to who it's going to go after and complex with, who's it going to be?
The calcium.
Yeah, definitely the calcium. We're going for the one with the bigger KF, right? So in this situation, do I really need to worry about interference from potassium ion?
No.
No, I don't. I don't have to worry about it, right? So potassium would not be an interferent. So what I'm looking for here is a large difference in KF values. So if we have a difference between, say, 2 or 3 or 4 or 5 orders of magnitude between the interfering ion and the analyte ion, okay, if that EDTA goes in there, it's going to preferentially bind to the analyte ion as long as that KF value is considerably larger than it would be for the interfering ion. So in this case, because of the size of the KF and the huge difference, what 10 orders of magnitude there basically, I don't need to worry about potassium ion being an interference here because the KF is so much bigger for the calcium ion than it is the potassium ion. Okay, so I can use KFs themselves as a means of selectively complexing a given ion. Okay, but is that going to work all the time? No, it's not, because I may have other ions in there whose KFs are around the same order of magnitude as calcium's or even bigger, right? So that could be problematic. All right, so I want to kind of go back to, I think it was John's idea of precipitating stuff out, right? You were the one that mentioned that, right?
Yeah.
So that's another thing we could do. We could precipitate out interfering ions. So in this case, we'd have a situation where KSP is going to win over KF. So this brings us to the issue of what I like to call competitive equilibrium. And we touch on it in dynamics. It's something we don't spend a huge amount of time on because it tended. But basically, we can get an idea of which equilibrium process is going to be favored by comparing K values. So basically, the more favorable K value for us is going to be the one that wins. Okay. But here's the question. How do I actually get something to precipitate out? I mean, how would I do that? So what are some options I might have for precipitating stuff out selectively?
Condense the solution. I mean, to reduce your volume. Yeah.
Okay, that's one thing I could potentially do. I can think of an easier way to do it. Well, one thing we could do, I think I mentioned it, is we could add some sort of a selective precipitating agent, right? So it would be some, for example, anion that I know will selectively precipitate with an ion I don't want, okay? So we can add a precipitating agent. So let's say, for example, my interferent is barium ion, and I want to get rid of it. Can you think of an ion I could add to the solution to precipitate out barium ion? In other words, I want to make something that's really, really insoluble.
No, I can't think of anything.
Sulfate.
Sulfate. Okay.
And as a matter of fact, if you wanted to do the calculation, you could. You could go back and look up the KSP for barium sulfate, and then you could compare that to the KF value for the formation of the barium EDTA. And you can see which one basically in its respective direction goes to the larger order of magnitude. Okay, and that'll tell you whether or not this would work or not. All right, but that's a basic idea that we could utilize here. So we could add some kind of a precipitating agent to take a specific ion out of solution. So one other option I'm just going to mention to you, and we'll come back more with it on Monday, and that is we can vary the pH of the solution. So basically, when we vary the pH, we're going to use hydroxide ion as a precipitating agent. So you'll remember, for example, that a lot of the simple metal ions will form insoluble hydroxides, okay? So if we form insoluble hydroxides, we can use pH as a means of taking the ion out of solution. That also helps us with EDTA as well, because remember, we form a more stable complex of the EDTA the more basic we go. So that one helps in both directions. We're making the KF bigger. We're also making the KSP more favorable or smaller, right? Because we are adding more hydroxide. I should say the KSP reaction, because the KSP is obviously going to be a constant. But I can use Le Chatelier's principle to push that reaction more toward the solid side. Okay, so for example, I think iron works that way. if I have iron 3+ in solution, I could add, for example, 3 hydroxides to that. And essentially what I'm going to get is FeOH taken 3 solid, right? Okay, and remember what that is. That's 1 over a KSP, isn't it? And a KSP is a really tiny number, so 1 over the KSP is going to be a really big number. So then I could compare that to the KF, okay, for iron 3+. And if it turns out 1 over KSP is greater than the KF of iron 3+, I could use this as a means of being able to eliminate iron as an interferent. Everybody see how I did that? And there's other
Yeah.
stuff we can do. There's other stuff we can do, but I just kind of wanted to throw a few examples out at you of some things we could do. So we'll come back on Monday and we'll talk more specifically about some of these means of being able to build some selectivity into the measurement. All right, any questions, guys? All right, so remember what's due on Tuesday. I will see you on Monday, obviously, but remember what's due on Tuesday. You've got your buffer homework problem to work out, the customized buffer homework problem. And again, look at that last buffer example that we did in class. That's a really good model to help you work through that problem. And then the last thing is to remember to have your kombucha lab ready for me. And I'll go ahead and post that next lab, which is the calcium EDTA lab. So you'll have that so you can get it into your notebook. By the way, I've started looking at the labs that you guys turned in. The data actually look pretty good. I'm pretty pleased with it. Your plots look generally good. I mean, the system is pretty much acting like it's supposed to. So I'm pretty pleased with it. A few interesting things popping up here and there, but I'm pleased. All right, guys, anything else? Okay, I will see you guys on Monday then.
All righty, thank you.
All right, you're very welcome.
See ya.
See ya.